So this section is the last section in chapter 11, that's section 11.8, and it's the derivatives of exponential and logarithmic functions. So I'm going to do a brief review of chapter 4, which is exponential and logarithmic functions. And how I'm going to do this is I'm going to go through the first 4 objectives, which are exponential functions, and then we're going to talk about the derivatives of exponential functions. And then we're going to come back and do logarithms and then do derivatives of logarithms. So section 4.1 is a refresher about exponential functions. And you've probably been looking at a lot of exponential graphs on the news lately, as I have. And exponential graphs grow the fastest of any of the functions we'll learn about. So we use them to describe situations where there's rapid growth. So here I have an example of the population in Placer County over the past 50 years, and it very closely follows an exponential growth pattern. So let's make a graph of y equals 2 to the x as an example. So we can see what the graphs look like. So I'm going to have x and y equals 2 to the x. I'm going to put my x-axis down here at the bottom so that I have more space for the graph. So when x is 0, y will be 2 to the 0, which is 1. So the point 0, 1 will be on my graph. And then if x is 1, y equals 2 to the 1, or 2. So the point 1, 2 will be on my graph. Then if x is 2, y will be 2 squared, or 4. So the point 2, 4. And if you're seeing a pattern here, this is called the doubling function. So there's definitely a pattern going on. So then when x is 3, y is going to be 2 cubed, which is 8. So the point 3, 8 will be on my graph. And then I've run out of room because if x is 4, y would be 16, and I don't have enough space left. So then let's also put some negative numbers for x, so we can see what the graph's doing over there. So when x is negative 1, y is going to equal 2 to the negative 1, or 1/2. So negative 1, 1/2 is a point on the graph. And then when x is negative 2, y will be 2 to the negative 2, or 1/4. So you can see as x goes farther towards the negative, you're going to get smaller and smaller and smaller fractions, 1/8, 1/16. So the shape of the graph is like this. Every exponential graph goes through the point 0, 1, because no matter what the base is, if x is 0, y is going to be 1. And then let's look at the range of this graph, the domain and range. The domain is all real numbers. You can put any x value into an exponential function and get a valid result. The range is positive y values only. You can never get to y equals 0 by putting a number x into this function. So in interval notation, we'd say from 0 to infinity. Y goes from 0 to infinity, but not including 0. Then there's no x-intercept, because this graph never touches the x-axis, but it has a y-intercept, and as we just said, the same y-intercept for every exponential graph. And then it does have a horizontal asymptote of the x-axis, which has an equation of y equals 0. So every exponential function has these characteristics if the base is greater than 1. So in this case, the base was 2. If it's 3, 5, anything greater than 1, you will get this shape. So this is the simplest exponential function, a base with x, the variable, as the exponent. So let's compare graphs with different values of a and see what effect that has. So I'm going to hop over to Desmos. And we use the hat for the exponential. So we say, let's do 2 hat, which is above the 6, to the x, and that's what the graph looks like that we just drew. So then let's see what happens if I do 3 to the x and see what changes. Well, you still have that y-intercept of 0, 1, but you can see that the 3 to the x graph grows faster. It's steeper. And then if we say 4 to the x, it's steeper yet. So when you make the base larger, the graph grows faster. Well, let's look at what happens if you have a base that's between 0 and 1. So suppose our base is 1/2. Oh, that causes the graph to reflect about the y-axis and be an always decreasing graph. So if A is larger, the graph is steeper. And if A is between 0 and 1, the graph is decreasing. So we saw, for example, 1/2 to the x looked like the reflection of the 2 to the x graph. So the graphs of a to the x with 0 less than a less than 1, so if a is any number between 0 and 1, your base, you still get your domain of all real numbers. So this is the blackboard bold notation for all real numbers. You still get that the range is positive numbers only. So in interval notation, that would be 0 to infinity, not including 0. You still have no x-intercept. And you still get the same y-intercept of 0, 1. So no matter what the base is, if the exponent's 0, the y value is going to be 1. And then we have the same horizontal asymptote of the x-axis, which is the line y equals 0. So let's see what happens if we look at Desmos at the graph of 2 to the negative x. So I'm going to do 2 to the power of negative x. And notice that I can't tell the difference between 1/2 to the x and 2 to the negative x. The graphs are identical. Let's see if we can figure out why that would be. So if I have 1/2 to the x, we reviewed the properties of exponents that say I could write that as 1 to the x over 2 to the x. And then we know that 1 to any power is always going to be 1. So I have 1 over 2 to the x. Well, we reviewed the properties of exponents that said that is 2 to the negative x. So 1/2 to the x and 2 to the negative x, those functions are identical and their graphs are going to be identical. A really common base for application problems is this number e, which hopefully you've run into before. You need to be able to find it on your calculator. If you don't have an e button and you only have an e to the x button, then you can find e by doing e to the power of 1. So I want to make sure you know how to find that on your calculator. So make sure you're getting about 2.7182818 and so on. It's an irrational number. So it does not have an exact decimal representation. It just has an approximation. So now that you know about limits, you can learn the actual definition of the number e, because it's the limit as n goes to infinity of 1 plus 1 over n to the power of n. So that's just, e is defined as that. It's e in honor of the Swiss mathematician Euler. And so he is the one that discovered this number and its properties, and so they named it e in his honor. So let's look at some functions and see if we can classify them as linear, quadratic, or exponential Well, as soon as the exponent has a variable, that's an exponential function. So number 1 is exponential, number 5 is exponential, number 4 is exponential, and number 6 is exponential because you see the x in the exponent. The number 3 is quadratic because I see a power of 2 on the x. And number 2 is linear. That's the equation of a line. So let's look at an example where we're just evaluating an exponential function. And I like to make charts where I put the information that I'm given. And in this problem, I'm given that x equals 7 corresponds to the year 2007. So I can see that x equals 0 is corresponding to the year 2000. So when I'm asked to find the assets in 2012, I can easily see that, oh, that means the x is going to be 12. So using proper function notation, I'm going to say a of 12. So everywhere I see an x, I'm going to put a 12. And I just want to make sure that you can operate your calculator correctly. So let's see what we get. And I'm getting about 616.817, and this is in billions of dollars. So make sure you can get that number with your calculator. Okay, and then we also have a different model for finding the scrap value of a machine by depreciating it in an exponential way. When we depreciated something previously, we did it in a linear way, a straight line depreciation where it was losing a certain number of dollars every year. Well, this way, we're depreciating it in an exponential way where it's losing a certain percentage each year. So this is the formula. So S is going to equal, C is the original cost. So I'm going to put 244,000. Then 1 minus. Then whenever you have a rate that's a percentage rate, you always turn it into its decimal equivalent to use it in a calculation. So it's going to be 0.15. And then n is the number of years. So we're going to have 1 minus 0.15 to the power of 12 times 244,000. And I'm getting about 34,706.99. So make sure you know how to get that on your calculator. So this is different from the linear depreciation that we calculated previously. It's faster depreciation at the beginning. So section 4.2 is applications of exponential functions. And there's two ways of expressing them. You can either have y sub 0, the beginning amount, e to the kt, using that number e that we just learned the definition of. Or they can also be written as f of t is y0, the beginning amount, b to the t with a different base. So y0 is always the beginning amount. And then the k is called a growth factor. So let's look at an example where we're just asked to use an exponential model where B is your balance on your credit card if you just make minimum payments. Okay, so your balance after 6 months will be B of 6 is 1,500 times 0.9604 to the power of 6. And I'm getting 1177.08. That would be your remaining balance after paying the minimum payment only for 6 months. So let's see how that changes if you do that for a year. And notice that you don't put 1 in for years, you have to put t in months. So you have to put 12, and you're going to have 1,500 times 0.9604 to the power of 12. And I'm getting 923.67. So it's going to take a while to get that credit card debt paid off if you continue just making minimum payments. Okay, so I'm going to stop this video here and resume in a second video so that they don't get too long.